In this video, I will demonstrate how to perform a standard multiple regression. And in standard multiple regression, what we're typically doing is taking two or more predictor or independent variables and then using those to try and predict a quantitative or numeric outcome, a single quantitative or numeric outcome. Now, in standard multiple regression, all of our independent or predictor variables are entered into the equation or into the model simultaneously. So each independent variable is evaluated in terms of its own predictive power over and above that offered by all the other independent or predictor variables. This is probably the most commonly used form of multiple regression, and you would typically use this approach if you had a set of variables, for example, personality scales or risk factors, and wanted to know how much variance in an outcome variable or dependent variable, like level of eating disorder or level of muscle strength, for example, they were able to explain as a group or a block. And so this approach would allow us to figure out how much unique variance in the dependent variable each of the independent variables explain. Now there are several assumptions with multiple regression. And one of the first is sample size. And typically the rule of thumb here is the larger the sample size the better, because as we're trying to make predictions about outcomes, we need to have enough variance or enough variability in our predictors as well as in our outcome to be able to make a good prediction. So one of the rules of thumbs that we use is we typically want about 15 participants per predictor variable. So if we only have two predictor variables, the absolute minimum number of participants we would have would be 30. And so as our number of predictor variables increases, the number of minimal subjects we should have. Now, if our dependent variable is normally distributed, which is, again, one of the assumptions we'll talk about in a little bit, then that rule of thumb of 15 per predictor variable is acceptable. If our dependent variable is slightly skewed, or if we have concerns about its distribution, then we probably want to increase that number. Okay. The next assumption is of multi-collinearity, and this refers to the relationship among the independent variables. And so when our independent or predictor variables are highly correlated to each other, that's the case of multi-collinearity, and we use an R value typically of 0.9 or higher to say that two predictor variables have multi-collinearity. Okay, and so we don't like to have multi-collinearity in multiple regression because that means we've got some redundant predictor variables, and that tends to make the model more cumbersome and less accurate when we're using more than one variable to measure the same thing. So we always will check for multi-collinearity. The next is outliers. We want to make sure we're screening for outliers. Multiple regression is very sensitive to outliers, whether they're very high or very low scores. And so checking for extreme scores should be part of our initial data screening process, as well as making sure we have accurate and complete data. So we should do this for both the dependent and independent variables that we're going to use in our regression analysis. And outliers can either be deleted from the data set, or perhaps we can generate scores through multiple imputation, or some of the other things we can do when we have missing data. Okay, the next assumption we have is that our outcome variable needs to be normally distributed. The relationship between the independent variable and the dependent variable needs to be linear. They need to be linearly related. And we also need to have similar variance on the dependent variable among our different predictor groups. So we need to make sure that that dependent variable has a normal distribution, is not skewed, and if that's the case, that usually takes care of that issue. But we also want to make sure that we have a linear relationship between the predictor variables in the outcome. Okay, so the example we're going to do here for the standard multiple regression is I have several data points, and what we're going to look at is how or if some predictor variables can predict the level of someone's perceived stress. So the variable we're going to use is our outcome is total perceived stress, or TP stress. So this is a numeric measure of someone's stress level. So a higher score indicates a higher stress level. And so for our predictor variables, we're going to use measures of control. In other words, how strongly someone feels they're in control of their emotions and their feelings. And we're going to use the measure called T-MAST, which is a measure of someone's mastery, that they feel they have control over, perceived control over events and circumstances. So how well they feel they can control things. So that'll be one of our predictor variables. And then the other predictor variable will be the perceived control of internal states, which is this TPCOISS. Okay, and higher scores indicate the person feels they have greater control over their internal states, like their internal emotions, their thoughts, and their physical reactions. So to summarize, we're going to use a measure of someone's perceived level of mastery, how well they're able to control themselves, and then also their perceived level of their internal states. And we're going to see if those two variables can predict someone's level of perceived stress. Okay, so our first step then is we get ready for this procedure is as we go through the steps, and as I'll demonstrate how we actually tell SPSS what we want to do, one of the first things we'll do is check the assumptions that we have, and then we'll go ahead and actually look at the regression model that's produced. So we want to go to the Analyze menu, then select Regression and Linear. So we're going to take our numeric dependent variable or outcome, in this case total perceived stress, and move that into the dependent variables box. And then our two independent variables, total mastery and that internal states measure, so internal states measure and then total mastery measure, move those into the independent variables box. We're saying that those are going to be our two predictor variables. Now just below that you can see where it says method. Make sure the enter method is selected, and this is the standard multiple regression where we put all the variables. If you had more than two, this is where we have all the variables entered into the model at once. And we'll talk a little bit about the difference between that and hierarchical or stepwise regression in a different video. We next want to click on the statistics button. Okay, we want to make sure we have the following selected: estimates, confidence intervals, model fit, descriptives, part and partial correlations, and collinearity diagnostics. Now those are going to help us determine some of those, whether or not we meet some of those assumptions. Okay, in the residuals section, we want to select case-wise diagnostics. Okay, and make sure that outliers outside is checked, and then 3 should be inside the standard deviation. So this is going to help us check for outliers that are beyond 3 standard deviations from the mean of our variables. Okay, once we've done that, we click Continue, and then we click on the Options button. And in the Missing Values section, check Exclude Cases Pairwise. And what this is going to do is if we have any subject that is missing one of the variables, whether it's one of the predictor variables or the outcome, they're going to be excluded from the analysis. Okay, we click on Continue. And we're going to click on the Plots button. Okay, and we want to move the variable that's labeled as star ZRESID, okay, into the Y box, and then the variable that's labeled star ZPRED, the one just above it, into the X box. Okay. Now in the section that's labeled standardized residual plots, we tick the normal probability plot, click on Continue. Okay, and then we click on the Save button. And in the section labeled Distances, we're going to select the first choice, the Mahalalobis distance, and also Cook's distance. Then we click on Continue, and then we click OK. And so here is our output. So the first step here is to check our assumptions. So the first assumption we want to check is the multicollinearity assumption. So in order to check the multicollinearity assumption, we want to find the table that's labeled correlation. So if we go over to our menu here in our output and click on correlations, it'll take us to that table. This is the table we see here. So what we want to see is if our independent variables show at least some relationship with our dependent variable. In other words, an R value greater than 3.0. So as we look at total perceived stress is our outcome, and we follow that over to our two predictor variables, we can see that both predictor variables have negative correlations with the outcome, but they're greater than 0.30. So in that case, both of the scales correlate quite strongly with our outcome, total perceived stress. Okay, we can also check that the correlation between each of our independent variables is not too high. So as we look at the correlation between PCO-ISS score and total mastery score, we can see that that's a 0.521. So we can see that our two predictor variables are correlated with each other, which is okay, but we don't want them to be higher than typically 0.7. So if there's too strong of a correlation, that might mean there's some multicollinearity or some redundancy in those two predictors. So when we have a case where we have a correlation greater than 0.70, we probably don't want to use both of those predictor variables. We probably want to omit one of the variables or maybe form a composite variable if we have two highly correlated predictors. So in this example, our correlation is 0.52 or 0.521 to be exact, which is less than 0.7, so we can use both those variables as predictors. Okay, so SPSS also performs some collinearity diagnostics for us. And so this is again is one of the assumptions we want to look up or look at. So this can pick up on any problems with multicollinearity that maybe wasn't picked up or wasn't shown to us in just the correlations that we just looked at. So what we want to find then is the table labeled coefficients. Okay, and so we click on that. And so two values are given to us in this coefficients table related to collinearity diagnostics. And the first is tolerance, and the other is VIF, or variance inflation factor. So tolerance, let's talk about that first, is an indicator of how much of the variability of the specified predictor variables is not explained by other predictor variables in the model. Okay, so if this value is very small, in other words less than 0.10, it indicates that there might be multiple correlations that are high, suggesting multicollinearity. So our value here in our two independent variables is 0.729. So that's well above 0.10. So we can say, at least in this measure, we do not have multicollinearity. Okay, so this variance inflation factor, we can look at that next. And this is basically just the inverse of the tolerance value. And when we have VIF values above 10, that would be a concern indicating multicollinearity. And as we can see here, our VIF values are 1.37, which is well below the value of 10. So both of these statistics give us an idea that we do not have multicollinearity. So we've met kind of the assumption of multicollinearity, in other words, not having multicollinearity. Now, if you do have multicollinearity, if these tolerance or VIF statistics were below or above the thresholds that we just talked about, then you're probably going to want to consider, again, removing one of these predictor variables or perhaps finding a different predictor variable. Okay, the next assumption we want to look at is for looking at normality, linearity, as well as outliers. And so one of the ways we can look at these assumptions can be checked by expecting the normal probability plot that we asked for. Now, in order to find those, we want to go down to our chart section. Okay, and the first thing we'll see is this PP plot. Okay, in a normal PP plot, what we want to see is our points, all our dots here, will lie reasonably close to this kind of line of best fit that bisects the chart here. So as we can see, we want this to be a reasonably straight line. It might deviate a little bit. But as we can see here, we have very little deviation from this perfect line. So it appears that we have a good fit on the PP plot. So there's no major deviations from normality. Now just below that, we can also look at the scatter plot that's produced of our variables. And what we're looking at is we want to see a roughly rectangular distribution. So if we look at all these dots, what we want to be able to do is pretty much draw a rectangle around all of these dots. And if we see a roughly rectangular distribution, then with most of the scores kind of clustered in the center, then we've met that assumption of linearity. Now, what we don't want to see is kind of a clear or systematic pattern to the dots where they're higher on one side versus the other. And so deviations from this kind of centralized rectangle shape suggest some violation of those assumptions. Okay, now outliers can also be detected from the scatter plot. And so typically we define outliers as cases that have a standardized residual, as displayed in the scatter plot, of more than 3.3 or less than negative 3.3. So with large samples, it's not unusual to find a few outlying residuals. But if you find only a few, it's probably not something you need to worry about or take action about. Now, as we look at this, we can see we do have some standardized residuals that are approaching -4 and are approaching +4, but these are a small number of residuals that are in that neighborhood. So we probably don't need to worry about that. Now, we can also check for outliers by inspecting the Mahalanobis distances that are produced by the multiple regression program. These don't appear in the output, but are presented in our data file as an extra variable at the very right-hand position of the data file. Now, to identify which cases are outliers, and we'll look at the data file in just a second, you'll need to determine the critical value using the number of independent variables as the degrees of freedom. So if we have scores that exceed this critical value, then we would consider them to be outliers. So first of all, in order to determine this, we need to determine how many independent variables will be included in our analysis, and we know we have 2. Okay, and then we need to use this number of independent variables, and we associate that with a critical value of chi-square. So for example, having 2 independent variables is associated with a critical value of 13.82. Having 3 independent variables is associated with a critical value of 16.27, and so on. So because we have 2 independent variables, the critical value for determining outliers would be 13.82. So to find out if any of the cases have this Mahalanobis distance value exceeding 13.82, we can go to the residuals statistics table. So we click on the residual statistics table and then go to the row that is labeled MAHAL distance. And so the maximum value in our data file is 13.897, which just slightly exceeds that critical value of 13.82. So to find out which case has this value, we can go to our data editor. So we go back to our data, okay, and we go to the data file, and then we go to select cases. I'm sorry, sort cases. And so we're going to sort by the new variable at the bottom of our choices here. The MAH_1 variable. So we're going to move that to the sort by box. Okay, and we want to sort by descending order. So it'll list the highest values first and then go down in order. Okay, so we click OK, and then if we go to back to our data window, we can see now that the highest score is now the highest distance score is now listed. So we have one score, one individual who has a distance score above our critical value. And so with the size of the data we have, it's not unusual to see a few outliers, and we only have one case. So in this situation, I really wouldn't worry about having one case that's only very slightly outside the critical value. If you find cases that are much higher than the critical value, you may need to consider removing these cases. And if you have a large number of cases that exceed that critical value, if you have more than about 2%, I would say, that exceed that critical value on the MAHA distance, then I would probably consider removing those. Okay, now the next thing we can look at, let's go back to our output file. Concerning any unusual cases we might have as we examine this, is in a table called case-wise diagnostics, which is just above the residuals statistics. So go to case-wise diagnostics. Okay, this presents information about cases that have a standardized residual value above 3.0 or below -3.0. So in a normally distributed sample, we would expect only about 1% of cases to be outside of this range. So in this sample, we have, in our example here, we have one case, case number 55, that has a residual value greater than 3.3. So as we can see, as we look at the table, we can see that their total perceived stress score of 14, they have a total perceived stress score of 14, but our model predicted they would have a score of 28. Okay, so clearly our model did not predict this person's score very well. They're actually a lot less stressed than predicted. Okay, so that might be a problem. So to check whether this individual case, this case number 55, is having any undue or oversized influence on the results from our model as a whole, we can check the value for Cook's distance given towards the bottom of the residual statistics table. So here down, we look down at, here's Cook's distance here. Now, if cases have values larger than 1, then that is a potential problem. Okay, so in our case, our situation, our example here, the maximum value of Cook's distance is 0.091. So that's obviously much less than 1. So that indicates that this individual case or individual subject is not having an undue influence on our ability to predict the outcome. Now, if you obtain a maximum value above 1, you should probably go back to your data file and sort cases by the new variable that SPSS creates that's called Cook's distance, or COO_1, and then look at each of the cases that are above the values of 1, just like we did with the Mahalanobis distance, where we sorted them by that variable from descending on down. So we might need to consider removing any cases that have Cook's distance greater than 1. Okay, so we've examined all of our assumptions here, and we seem to have met all of our assumptions. So we can move forward now with evaluating the model that we created to see how effective this model is and whether it's statistically significant and how accurate it will be in its predictions. So our next step then is to actually evaluate the model. So we want to go to the model summary box. So we click on that, and that'll take us to the model summary. Okay, and we want to check the value given under the heading R square. Okay, now this tells us, this value right here, this tells us how much of the variance in the dependent variable, perceived stress, which is our outcome, is explained by the model. So we've got our two variables, mastery and that PCOISS variable. So we want to know how much those two variables explain stress level. So in this case, the value is 0.468, as you can see here. Now, expressed as a percentage, we just basically just multiply that number by 100. This means that our model, using our two predictor variables, explains about 46.8% of the variance in perceived stress. So whether someone's going to have a high stress score or a low stress score, about 47% of that variance is explained by these two predictors, which means that more than 50% of the variance in stress is explained by other things. So, but this is actually a pretty respectable result. If we can get close to 50% of the variance explained by two predictor variables, that's pretty good. Okay. Now, you also can see an adjusted R-square value right next to the original R-square value that we looked at. Now, when we have a small sample size, the R-square value in the sample tends to be a little overestimated. It's a little optimistic overestimation of what was probably really happening in the population. So the adjusted R-square statistic corrects this value to provide a better estimate of what's actually happening in the population. So we have a small sample size. If maybe you're right at that 15 subjects per predictor variable limit, you may wish to consider reporting the adjusted R-square versus the normal R-square. Now, the next step then is to assess the statistical significance of our result. In other words, is the model a statistically significant predictor of the outcome? Does it make accurate predictions in the way that we can say this is a true prediction of what would happen in the population? We want to look in the table labeled ANOVA. So this tests the null hypothesis that multiple R in the population equals 0. So in other words, the model cannot predict accurately the outcome. Now the model in this example has a p-value less than 0.05. So we would say that there is statistical significance for this model. In other words, the model does a good job at predicting the outcome better than just chance. Okay. Now our next step, our third step, is to evaluate each of the independent variables. So the next thing we want to know is which of the variables in the model contributed most to the prediction of the outcome. And so we find this information in an output box labeled coefficients, which is right below the ANOVA box. Okay. Now we want to look in the column labeled beta under standardized coefficients right here. And we want to compare the different variables as far as their beta level. And what we want to look at, make sure we're looking at, is the standardized coefficients, not the unstandardized coefficients. So it's important that we look at this column, standardized coefficients beta. Now standardized means that these values for each of the different variables has been converted to the same scale so that we can easily compare them. Now if you're interested in constructing a regression equation, in order to create the equation to where if you know the value for PCOISS and we know the value for total mastery, can we predict our total stress, we would use the unstandardized coefficients and we'd use these values in this B column to actually create a multiple regression equation. Now in this case we are interested in comparing the contribution of each independent variable. And so we're going to use these standardized coefficient beta values. So we look at the beta column and find which beta value is the largest. And we're going to ignore sign. It doesn't matter if it's positive or negative. So in this case, the largest beta coefficient is 0.424, and that comes from the total mastery variable, that predictor variable. So that means that this variable makes the strongest contribution to explaining the outcome when the variance is explained by all the other variables in the model, and that's controlled for. So that individual variable does the best job of explaining the outcome. So the beta total for our other predictor variable, PCOISS score, is slightly lower, so it made less of a contribution, but it still made a fairly large contribution. Okay, now for each of these variables, we can also check the statistical significance of their contribution, and so we find the column that's labeled SIG. Okay, and this tells you again whether the variable made a statistically significant, unique contribution to the prediction model. And this is going to be very dependent on which variables are included in the equation and how much overlap there might be among these independent variables, how much collinearity there might be. So if the significance value, the SIG value for our two predictor variables, is less than 0.05 or 0.01, depending on how stringent you want to be, then we can say that the variable is making a significant, unique contribution to the prediction of the outcome. If it's greater than 0.05, then you can conclude that the variable is not making a significant, unique contribution to the prediction of the outcome. And again, this might be due to some overlap of the predictor variables, some multicollinearity. In this case, both total mastery and total PCOISS score made unique, statistically significant contributions to the prediction of the outcome. Now, the other potential useful piece of information in the coefficients table is the part correlation coefficients. So we look over here where it says correlations, and we see part. This is sometimes also referred to as semi-partial correlation coefficients. So that might be a little confusing. You might see that in the literature. Now, if you square these values, these part correlation values, you get an indication of the contribution of each individual variable to the total R squared. So in other words, it's going to tell you how much of the total variance in the outcome is uniquely explained by that variable, and then how much R squared would drop if we removed that variable. So our R squared, if we remember, was 0.468. So if we removed the total mastery variable from the prediction, then our R squared would drop by 0.362 and would only end up being 0.106. So it would be a very small R squared. So now we can also again take this value and square it. So if we square this value, multiply it by itself, we get 0.13, indicate that mastery uniquely explains about 13% of the variance in the total perceived stress scores. Now you may have noticed that our R squared value is not the total of the two part correlations added together. So the R squared value for the model does not equal all the squared part correlation values. Now this is because the part correlation values represent only the unique contributions of each variable with any overlap or shared variance removed or partialed out. So the total R squared value, however, includes the unique variance explained by each variable and also the variance that is shared. So in this case, our two independent variables are reasonably strongly correlated. Therefore, there is a fair amount of shared variance that is statistically removed when they are both included in the model. Now, one last thing we can look at when we think about developing a regression equation to actually be able to predict someone's total stress level, another piece of information that's important is the standard error of the estimate. And this is basically gives us an idea of how much our prediction might be off. And we can think about this in terms of plus or minus. So if we made a prediction of someone's stress level using total PCOISS score and total mastery score, the prediction of their total stress might be off by about 4.27 points. So that gives you an idea of how much variability there might be in our prediction. Now, it doesn't seem like a whole lot of variability, a score of 4, but certainly the larger that number is, the more variability there might be in the equation. So the more statistically significant a equation is, and the higher the r squared value is, typically the smaller the standard error of the estimate. Okay, so to summarize, the results of our analysis allow us to answer a couple questions about our situation here, our model. So our model, which includes this mastery score, in other words, how well people feel like they can control external events and also control their internal states, their emotions and their reactions, explains about 47% of any variance in a perceived stress level. So of these two variables, mastery makes the largest unique contribution, and PCOISS also made a statistically significant contribution. So we had a statistically significant model that allowed us to predict perceived stress using two predictor variables. Both of these variables had statistically significant contributions to this model, with the mastery variable having the larger contribution of the two, but still both having statistical significant contributions. So this is a great example of how we could run multiple regression. Now we could have obviously more than two predictor variables if we wanted to. The process is pretty much the same. It just gets a little more complex as we have to examine more layers of variables as we look at assumptions and also kind of determining which variables are making the most contribution. So hopefully you learned something from this presentation, and hopefully you have good luck with this technique when you do your own research.